Okay, so it's just gone 7 o'clock. Let's kick off, shall we? So, hello, good evening, and welcome. I'm Neil Johnson, and I'm your host for tonight's Audio Engineering Society UK section webinar. Do you know your gigabits from your megabytes? Can you tell a VLAN from a spanning tree? Do you know how to daisy chain Dante ports safely? In tonight's talk, Andy Cooper from Yamaha's R&D Centre here in the UK will guide us through the digital networking jungle. So without further ado, I am now going to try to switch over to Andy. One moment, please.
Thanks for joining this webinar. My name's Andy Cooper from Yamaha's Research and Development Centre in the UK. I'm coming to you from our video studio in the town of Milton Keynes. Things sound engineers need to know about audio networking. That's our topic for today. Should we start with a little joke? You know, when sound engineers do a microphone check, they go 1, 2, 1, 2, 2, 2. Well, they never count to 3, you know, because normally when you count to 3, well, the roadies have to start lifting something. But how do network engineers do a microphone check? Well, I think they would go 255, 255, 255. If you don't find that funny yet, hopefully you will in a bit after I've explained a few things. Here's our agenda. We're going to learn the basics of networking, cables, IP addresses, subnet masks, DHCP. What is all that? Then we're going to learn how traffic can be optimized to make your network efficient. We'll learn about Unicast and Multicast transmissions. We'll discover QoS and IGMP Snooping. Then I'll explain a bit about network design features like VLANs, trunks, spanning tree protocol, and lags. So we've got a lot of strange things to discover, and I'll let you know how useful they are in audio networks. So let's start with cables. You've probably heard of Cat5, Cat5e, Cat6 and Cat7 cables. What's the difference? Well, a couple of things. Number of twists per meter of the pairs in the cable. The higher the number, Cat7 has more twists per meter than Cat6, for example. And then the type of shielding between each pair of wires in the cable as well. But they all have the regular RJ45 connectors, either shielded or unshielded. Shielded is mostly recommended by manufacturers because it reduces the amount of electromagnetic interference. Though, to be honest, unshielded cables are easier to work with if you make your own terminations. Learn the pin-out configuration, you know, the order of colors and stripes. Learn it, because it's not so intuitive, but it's a good thing to know when you make your own cables. Then another thing is to check what type of copper is in your cable. Is it solid or is it stranded? Stranded cable can be quite flexible, so it lays down well on the floor of a stage, for example, or so it can be neatly placed in a rack. Though stranded copper is not so efficient at carrying your data long distances. So if you need to make use of the 100-meter limitation of copper, it's best to use solid copper, which is less flexible, but yeah, more efficient with your data. So there are advantages. If you need to go longer distance than 100 meters between your devices, then you should use fiber optic cable, whether it's rugged, you know, with special connectors for mobile or touring applications, or whether it's much smaller and lightweight for installations. No matter what type, it's the same kind of glass inside, just here with more protection. You should look for these standards though. For multi-mode fiber, you should look for OM3 or OM4 that has good enough quality glass. For single mode fiber, look for OS1 or OS2. Then you'll know they are good enough quality to carry the type of data you need in a audio or media network. Now let's move on to IP addresses. We're going to take a look at the difference between static, auto, and DHCP addressing mechanisms. We'll have a brief look at subnet masks and gateway addresses. So you find all of these three in the configuration of a network device like a Yamaha mixing console, which this picture is taken from the screen. So what is an IP address? Well, just like a mailing address, if you want to send a friend a birthday card, you've got to write down the county, the city, the street name, and the house number. It's the same with the IP address. But the first number of the IP address represents the state or the county, let's say. The second number in the address represents the city. The third number represents a street, and the fourth number represents a house. And each number can be from 0 up to 255. So you've got 256 houses in each street, 256 streets in each city, and 256 cities in each state or county. So you can work out there's over 65,000 houses in each city and over 16 million houses in each state. So your network can be pretty big. Let's take an example. A standard IP address used by a lot of audio networking equipment and home or office equipment is this 192.168.0.128. So in this case, we are in state number 192, city number 168, street number 0, house number 128. So it's our house in the middle of the street. Some IP addresses are not available for AV networks to use. They are reserved for other certain specific companies, or they're reserved for the World Wide Web. There are several ranges of IP addresses that are called private addresses that can be used in your home, in your office, or by your audio or AV network. This is why we often see an address starting with 192.168 in Wi-Fi networks, for example. Or you could see an address starting 10.something. Or you may notice that Dante primary networks by default use 169.254.something, and secondary networks use 172.31.something. Well, those networks are available for us to use in any private network. That's any network that is not directly connected to the internet, let's say. So now let's talk about subnet mask, because it's quite important to understand this. A subnet mask limits the size of your network. Just like when you wear a mask, you hide a part of your face. A subnet mask will hide a part of the network. So a typical subnet mask you find could be 255.255.255.0. That means you have 256 states hidden, 255 cities hidden, 255 streets are hidden, no houses are hidden. So your network has 256 houses in just one street, in one city, in one state. So your network is limited to 256 devices with this subnet. That makes it easier to handle. Generally, Dante networks and other AV networks have a subnet of 255.255.0.0. That means you've got 256 streets, each with 256 houses. So now your network can have over 65,000 devices in it. But actually, some addresses are reserved for management and administration. So numbers 1, 254, and 255 are not available for regular audio kind of devices. So still, we have at least 65,000 devices available in AV systems. So they can get as big as you need. Now, subnets or subnet address is actually a series of ones followed by a series of zeros. IP addresses are all binary. but we find them easier to understand when we write them as numbers, up to 255. So 255 in binary is 8 ones. So here, our subnet used by Dante is 16 ones followed by 16 zeros. Now, the IP address represented within the ones, so the first two sets of numbers, in this case, that is our network address. And every device within the network will have the same network address, the same first two numbers in this case. Then the host address is the numbers represented by the zeros. So the last two sets of numbers in this case. And here, all the devices will have different numbers. So in any network, every device will have the same network address and a different host address. I hope that's clear to understand. Another thing we need to understand is the class of a network. Or you may hear people talking about, what's your class of network? Or is it a class B network or class C? Let's explain. First, a class A network can have millions of devices. It has the subnet 255.0.0.0. Sometimes you'll write the IP address, then a /8. That means a subnet has 8 ones in it. So it's just 255.0.0.0. A class B network can have thousands of devices. It has a subnet 255.255.0.0, 16 ones. So a Dante network is generally a class B network. Then a class C network can have a couple of hundred devices. Subnet is 255.255.255.0. It's got 24 ones in the subnet, so /24. So that's generally the stuff we need to know about IP addresses and subnets. You might also see gateway addresses in devices. They're not normally needed, but a gateway address will point the data to the data that needs to reach outside of the network, maybe to access the internet or something. The gateway address is the address of the device you need to get to before you reach the outside world. So in home networks, office networks, it's the address of your Wi-Fi router. And it generally ends with a .1, like you see here. Another thing you might see is DNS server, and then space for an IP address. Again, in most AV networks, you don't need the DNS server address, and in home and office networks, it's generally the same as the gateway address, so your Wi-Fi router will do your DNS serving. What it is, it means domain name system, and it's actually a translator between IP addresses and recognizable names. You know, the internet is based on IP addresses, but if you want to find out information about a Yamaha product, you don't type in a certain IP address in your browser, you type in yamaha.com and it takes you there because there's a DNS server that knows to translate yamaha.com into a certain IP address. I have no idea what it is, and it may change from time to time, but DNS servers know how to translate. So they do that work for you. So it's internet related, basically, so we don't need it in most networks for audio or media systems. Now, every device in a network then needs an IP address, otherwise you can't send and receive data. If you've got a lot of devices, you don't want to have to give everything an IP address manually. Thankfully, there's automatic mechanisms to do the job for you. So, called zero config, or you don't need to do anything. Zero config or link local is when a device automatically starts using an IP address starting 169.254 with a subnet 255.255.0.0. You'll use it when you connect a computer to a network that's not connected to a DHCP server, which I'll explain in a minute. And that address type is used by Dante devices by default as well. So when you create a Dante network, maybe if you see on the screen here, everything starts 169.254, then random numbers after that. So that's great. You don't have to do a lot of manual management. But a DHCP server is useful. All your office and home networks will have one, probably built into the Wi-Fi router. And it's where every device is given an IP address, and it ensures every address is different. So in this example we see on the screen here, every device is given a network address 10.0.1 and a host address of a different last number. Here we see they start at 51 up to 55. So a DHCP server provides IP addresses and subnet masks and gateway addresses to every device in the network, and it avoids duplicates. So it can be very useful. Some devices, though, need a static IP address, or sometimes people want to use static IP addresses, but it takes time, especially if your network has a lot of devices in it. To assign an IP address manually takes time, and you can make mistakes. So avoid it if you don't need it. Sometimes, though, you do need a static IP address. In that case, what you can do is limit the range of your DHCP server. So here we limit it to go up to number 199, for example. Then you can use a static IP address, maybe with a last number above 199, to make sure you don't get any duplicates when you're combining static addresses with automatic addresses. Now, did you know some devices have network ports that have more than one IP address? So an IP address is not specific to a physical connection, but you can have multiple kind of logical IP addresses within one physical port. Here's an example from the back panel of a Yamaha CL or QL mixing desk. You've got a Dante primary and a Dante secondary port, and you've got an extra network port for communication. Now, a lot of Dante devices can work in what we call daisy chain mode, where you don't have redundancy, but you have two ports. And in that case, those two ports share the same IP address. And by default, it's going to be 169.254.something.something, unless you use a DHCP server. So you've got an address for your Dante audio and synchronization. Then you've got another address for device control. If you want your mixer to control through the Dante network, but control another device like a wireless mic receiver or an amplifier or mic preamps, then it needs another IP address for the control. In this case, it's also automatic or DHCP and is in the same range there, 169.254. The third port there is for mixer control. That's separate, and that has a static address. The default one is shown there. That is for if you want an iPad or computer software to remote control the mixing desk. So that's handled separately, static. Now, if we switch the device into redundant mode for Dante, then you have a primary port and a secondary port, and we have another IP address, automatically in the range 172.31.something, but again, you can use a DHCP server to specify it as something different. But now you see, one physical device is actually having 4 IP addresses at the same time for different tasks. So you really have to know what you're doing when you want to work with all of those in one system. Right, that's it for IP addresses. Next, we're going to move on and we're going to learn about how traffic can be optimized. So Unicast, Multicast, QoS, and IGMP Snooping. Remember, at the end, we're going to have plenty of time for questions, so please keep that in mind, and maybe I'll have more questions about what's coming up. We'll see. So, I'm going to help answer these questions. Why should network traffic be optimized? And when should traffic be optimized? How can you discover a device's limitations? And how do you know when the network gets full to capacity? Let's start with the device's limitations, which relates to bandwidth. So understanding your network bandwidth is very important in various parts of the network. Firstly, each device has its own bandwidth limitations in how much data it can transmit and receive. Also, every port in a switch has bandwidth limitations, maybe 100 megabits per second for small and older switches. Most of these have 1 gigabit per second, but some ports can carry 10 gigabits per second of data, like through their fiber ports. Though you can get switches that can carry 100 gigabits per second of data as well. That is possible. So you've got to understand the limitations. How much bandwidth is needed? Well, for audio, let's consider Dante audio networking tends to transmit audio in blocks of 4 channels. 4 channels at 48 kilohertz 24 bits will take about 6 megabits per second. 64 channels at the same sample rate will use up 96 megabits per second. 4 channels at 96 kilohertz then will be about 12 megabits per second. 96 channels at 96 kilohertz will take up about 288 megabits per second. Just to give you an idea. Let's compare that to video. How much bandwidth does video take? Well, a typical IP security camera will take just 2 megabits per second. It's going to be quite heavily compressed. An SDI camera at 480p, that will take about 540 megabits per second. That's DVD quality, including 8-channel embedded audio. A HD SDI camera at 720p, that'll be about 1.5 gigabits per second, uncompressed. And 4K video, that's huge. At 60 frames a second, it's 12 gigabits per second. So raw 4K data is too much for any of my network to handle. That's where you need those 100 gig ports. So that gives you an idea. How do you discover the limitations of your audio networking devices? Well, if you have Dante controller software with Dante devices, it's quite easy to discover. The Dante controller software will let you know how many flows can be transmitted and received. Each flow can handle up to 4 audio channels if it's Unicast. We'll come to Unicast Multicast in a minute. Anyway, each device, the smallest Dante devices, perhaps like this one, can receive up to 2 flows or transmit up to 2. That means it can receive audio from up to 2 devices, and it can transmit audio up to 2 devices. The largest Dante devices can communicate with another 128 others. They could receive audio from 128 different devices. Most Dante devices, though, most of these around here, can handle 32. So this mixer can receive audio from 32 different transmitters, and it can send audio to 32 different receivers. So, back to Unicast and Multicast. Dante transmission by default is Unicast. Actually, most network data is Unicast by default, from one transmitter to one receiver. So, one transmitter to one receiver. That's convenient in live sound too. From one microphone, wireless mic system to mixing desk, for example, or from one mixing desk to one amplifier. But sometimes you might need multiple Unicasts. So one microphone might need to be sent to 2 or 3 mixing desks. One for live sound, one for recording, one for broadcast, for example. So therefore the transmitter has to work harder, sending 3 sets of data in this case. So sometimes you're going to need multicast transmission. So let's take this example. One mixing desk in a sports stadium. Maybe there's 50, maybe 100 amplifiers all needing to receive the same signal. Well, the mixing desk can only communicate with 32. So multicast is the solution. You create one multicast transmission, and that is distributed by the network switch to every other device in the network. So then one transmitter can go to all devices in the network, which can include 100 more amplifiers. So multicast is your solution there when you want to transmit from one to many. But what if your multicast transmission is high bandwidth? You can run into trouble. Look at this example here. If you've got a camera which has a 1 gigabit per second output port, let's say one HD SDI stream is 700 megabits per second. Well, therefore, it cannot send to two different devices, Unicast, because 700 megabits times 2 is 1.4 gig, which is too much. So if you want to send the output of one camera to two devices, a screen and a projector, in this example, you have to send multicast because there isn't enough bandwidth for two Unicast. So the camera sends one multicast to the switch, and the switch duplicates the multicast to both receiving devices. That's your solution. But the trouble with multicast is it goes everywhere, even to the places where you don't want it. So if you have a 100 megabit device, that's going to receive 700 megabits per second, but it can only handle 100. So that's going to be overloaded and isn't going to work anymore. So you've got to be really careful. Or use a network switch which can manage your multicast bandwidth. Let's take a look at that. That is IGMP Snooping, Internet Group Management Protocol. The network switch will manage your multicast and stop it from going to the places that don't need it. Snooping is like friendly spying. The switch is listening or looking at all the data coming to it, recognizing the type of data it is and checking where it needs to go. So it will only send the video to the devices that need to receive it. It won't send the multicast video to your audio devices. Nice solution. And you can keep an eye on the bandwidth on Dante controller as well, like you see there. I'm going to try and do a little practical example now so we can see what happens. So this is a 100 megabit device and it's receiving audio. If I turn up audio on this mixer, there's a little bit of sound coming from this speaker. So it's coming out of my phone into this device, from that device to the mixing desk, from the mixing desk through this switch to this output here. See, if I unplug it, analog audio going to the speaker, just to prove to you that it's there. So if I add a lot of multicast, this cable here is carrying almost 100 megabits per second of multicast. It's actually a multi-track recording from my computer there. If I add this in here, let's see what happens, or hear what happens. Now the audio has stopped. And it's because of that extra bandwidth. So if I pull that cable out, the audio comes back. So what I can do, because this switch is an intelligent one, I can switch on IGMP Snooping and the audio will come back to that. So I can come to my screen, which I've just realised is off the view. Oh, maybe it's coming back in. I have a lovely cameraman called Tim who's helping. So we can see on the screen here that this is Yamaha's LAN monitor. It's telling me the switch port is overloaded. So I can open up the graphic interface for that switch and I can go to what is called Dante optimization and I can just switch that on. And that will enable the IGMP snooping. And the audio comes back again, as you can hear there. So now the multicast is blocked from going here because that doesn't need it, doesn't want it. Great. So, with IGMP snooping blocked, the multicast only goes to the destinations that you tell it to go to. So it follows the audio patching you make in your Dante controller software. Then you can mix low bandwidth devices with high bandwidth devices successfully. On a regular network switch, you can see examples here on the screen of how IGMP snooping is set up. It's pretty complicated, lots of different settings to make. It's quite tricky. Which is why Yamaha has done it with a simple on-off with the switches to get them quickly optimized for working with Dante. Now those other questions I asked earlier, why should traffic be optimized and when should traffic be optimized? Well, you know, when you're driving a car on a street, there are lots of traffic lights, aren't there? And that's to optimize the traffic, isn't it? So as traffic increases, you need more and more control, more and more lights, let's say. In a data network, if your bandwidth is approaching 80% of capacity, then we start needing to have some kind of control on the data. So more important data is allowed through, whereas less important data can be paused and sent when there's more space available in the bandwidth. Think of it like this. Do you remember those times when we used to be able to fly and queue up and board a plane? And you know, first class, business class could always go on the plane earlier. They could overtake the queue of economy people. Well, that's kind of how it is in a data network. So your synchronization data for keeping all your devices in time synchronized, that's the most important data. And that's like your first class traveling. As soon as it arrives at the switch sends it on to its destination. Then audio data and video data, that's important, but not the most important. That's like your business class. So once the first class queue has finished, then the business class guys can board and travel. Economy, they just have to wait until there's space for them to go. That's less important. Non-media data, let's say. So all your network data can have different identification tags assigned to them. So synchronization data will have one type of ID tag, audio and video data another type of tag, control data another. And your managed switches will recognize that type of data and will know what data is more important than the others. So each switch has a kind of table of code points or IDs. It's often called DSCP, Differentiated Services Code Points. And there are 64 types of data. You can assign them different levels of priority. Some switches have 4 levels. These switches have 8 levels of priority. So you put the higher priority to synchronization, next highest to audio, video, lower priorities for control data. And then the switch knows what's important and what isn't important, what data to forward quickly and what data can be paused until there's space. So that's possible, and that's how you program it in a regular switch. Here are the code points for Dante. So number 56 for synchronizing, number 46 for audio, number 8 for control and monitoring. That's how you would set it up on a regular switch. On Yamaha switches, it's on by default or included in that Dante optimization. One button to do it all. So that's really convenient. But like I said, this only comes into play when you're reaching about 80% of the capacity in your network. So generally speaking, that's not necessarily used. You can probably realize that IGMP snooping is much more important in your data management to stop multicast traffic going to the wrong places. So that's part 2 done. Next, part 3, we're going to understand some more network design features. Thanks for sticking with me through this. I know I've been moving through all of the topics quite quickly, but hey, there's a lot to fit in this short time. But remember, the question and answer section coming in a little while. So now I want to talk a little bit about network design topology. You might hear people talking about core edge networks or core distribution edge networks, where the core is a central switch with high bandwidth and the edge switches probably have lots of ports with lower bandwidth, where all your devices are connected to. Or you might hear people talk about spine leaf configurations, where you have several core switches arranged in a spine and then leafs coming off the spine, which are like your edge switches where all your devices are connected. So a couple of different ways, but they would typically be used in much larger networks. A lot of audio networks are quite small, maybe just between 1 and 5 switches totally. So you can make a short daisy chain like this with 3 switches and 2 cables. Maybe you've heard people talking about redundant rings, and some non-IP digital audio systems are made of redundant rings. Well, you can do the same with switches if they support spanning tree protocol, or STP. Maybe you've seen RSTP, which is rapid spanning tree, or MSTP, which is multiple spanning tree. Anyway, you can create a ring with switches and one cable remains temporarily blocked to avoid any sort of data feedback loop. And then when one working cable gets cut or broken, that temporarily blocked cable will start working again. So all the devices keep communicating with each other. One thing to bear in mind though, it can cause a couple of seconds of silence when this occurs. So it's not a perfect network for redundancy. There are better ways that we'll come to in a minute with systems like Dante. But first, let me introduce virtual local area networks, or VLANs. This is where you can separate different types of data, different types of devices, but they can still share the same hardware. So in this audio system, we've got the green devices, which are inputs to mixing desks, and then you've got the orange devices, which is the computer controlling amplifiers. In a typical touring system, you'd have 2 different individuals taking care of them. So they can look after their own systems without interfering with each other, not seeing each other's systems on the network, but sharing switches. The switches are segmented into VLANs, an orange VLAN and a green VLAN in this case. You know what VLANs remind me of? Pizza. Actually, a Four Seasons pizza, Quattro Stagioni. You have one pizza in 4 segments, different ingredients in each segment, there's no overlap. You never find a mushroom in the artichoke zone. That's just like VLANs in a switch. One switch with, well, it could be 4 divisions, 4 VLANs, it could be more, it could be less. But that's where your data is split and separated, but you share the same hardware for efficiency. Maybe you noticed though, there was one cable for each VLAN, so you end up with more cables between your switches when you use VLANs. But you don't have to. You can use things called trunks. So, you know, a trunk road links 2 cities together with multiple lanes of traffic. A trunk in a network will link 2 switches together and carry multiple VLANs through one cable. You just have to be careful not to overload the bandwidth. Because if your bandwidth of your trunk is 1 gigabit per second, then you should make sure both VLANs are, when combined, are not overloading that. So often you would want to use a trunk with higher bandwidth ports, maybe 10 gigabits per second, for example, like some of these switches have with their fiber optic cables. But it can be a risk. All your data is in one cable. If that's cut, all your data is gone. So there's a solution, and it's called link aggregation group, where you combine 2 or more cables to perform the same function, to have the same link. It's like adding lanes to your motorway, which can be used either for redundancy or for allowing more bandwidth. 2 cables will double the bandwidth available. But if you don't need the extra bandwidth, you can use it for redundancy. Let me do a quick demonstration. Back to our audio. So the audio is still coming through the same system as before. My mixing desk and I/O unit are in this bottom switch down here. The output is coming through the top switch here. We have one red cable linking those 2 together. Now I have programmed a trunk into these switches and a link aggregation. I can connect a second cable here. But first let me just show you, if you pull out the cable, it stops the audio, as you would expect. Now I'm going to add a second cable. So the audio is back, showing that's working. Add a second cable. Now I have some redundancy. If I pull out this first cable, there might be a little glitch, but the audio will continue. Says he, the audio will continue. There it is back again. So, as you heard there, again, it's not perfect redundancy, but it's pretty good. The system brings the audio back, quicker than you have time to fix the problem manually. So that's link aggregation. 2 cables or more for redundancy or for increased bandwidth. But there's still a better way for redundancy in a system like Dante. You can have full redundancy, including redundancy for your switches. In this case, you have double the number of switches and double the number of cables. Then if any switch loses power, no problem. If any cable gets cut, no problem. It just keeps on working. So I'm setting that up with another system here. I'm just moving my audio to this device. This device is sending audio to my mixer here. My mixer is sending the audio to this amplifier, which I just need to take off standby, which I can do through the network because it's controlled from there. Then the audio will appear on this speaker here. Once that's on, then this is my secondary network here, and I'm going to connect it to these. So we can hear that audio now coming through the primary network. This is the primary network here. So now I connect the secondary network to this switch. So we see the status there, that's connected. Actually, I can look on Dante controller, and we'll show a close-up of this in a moment, where we can see the primary and the secondary status on the screen. So wait for that to settle. Now I know that's settled. I can unplug any primary cable and it will have no effect on the audio at all. Any cable that I unplug, it keeps working. Now what's the worst cable you can unplug? Well, it's the power cable to the switch. So I'm going to do that. This is the primary switch. I'm going to pull the power out. You'll see the lights go off. Now that's gone, but the audio keeps working through the secondary. But of course, if you unplug something from the secondary as well, you can't protect everything. So unplug the secondary and the primary and it's gone. But hey, it's plugged in and it's back working. This just takes a minute to boot up and get going again. So that's almost out of time now for everything we've learned. So we've gone through the basics of networking, cables, IP addresses, subnet masks, and DHCP. We've learned about traffic optimization, unicast and multicast, one to many, quality of service, and IGMP snooping, blocking your multicast from places where you don't want it. And then we've talked about network design features, VLANs, trunks, spanning tree, and link aggregation. One last thing I want to show you just before we move on to questions and answers, and that's loop protection. So yeah, now this switch is working again. Have you ever connected both ends of one network cable to the same switch and then everything has just gone wrong, stopped working? If you haven't, you probably will do at some point. I certainly have done. It kind of causes a huge feedback loop in your switch and everything overloads and kind of crashes. So some intelligent switches have loop protection to stop that problem from occurring. Thankfully, this one does just that. The other end of this cable is in the back end of the switch. When I connect this, there might be a little break in the audio. We'll see. and the switch will find the port that's causing the problem. Actually, there wasn't a break in the audio at that time. So we are finding our loop, and we are saved from our own stupidity. Well, thanks so much for watching. It's been wonderful to have you with me. I hope you've learned a lot. Let's move on to the Q&A time.
Okay, well, thank you very much, Andy. That was a fascinating talk. Put some more light on. Covered a lot of ground. Yes, that's about 1 year's worth of communications theory thrown into 45 minutes. Network theory, yes. Good. So there's been lots of chats, and we've got a couple of questions to see what's on the chat. Pizza now, yeah, I'm getting hungry now, so thank you for the pizza analogy. And yeah, pizzas. I'm keep thinking of pizzas. So we have a couple of questions from the audience just to start things rolling. So John is asking for a link or post to a glossary that covers all of these terms and the differences or similarities with AES 67 terms.
Yeah, I've seen that. Actually, I don't think you'll find the answer in a glossary, because three of those four terms, I think, are sort of different colloquial ways of describing the same thing. If my understanding is correct, that is. So, yeah, you've got channels, that's like physical audio channels, as you'd see on a mixing desk or a patch bay. But streams, flows, and groups, I think, are all different names for the same thing. So flows is generally the term Dante uses for grouping channels together into IP packets, which, you know, it is like putting 4 sheets of paper into an envelope and then sending the envelope to another place. That is, the envelope is a flow, and there's 4 channels of audio in it. And that's how the network sends the data in envelopes, let's say, or packets. So Dante calls it a flow. AES 67, a lot of manufacturers will call it a stream, but it's basically the same thing. And perhaps other manufacturers or other people or other organizations would call it groups, but it's all one and the same. So anyway, the question seems to be about bandwidth, doesn't it? So I always give the recommendation of 1 gigabit Ethernet is suitable for up to 400 audio channels when they're in 4-channel flows. So therefore 10 gigabit would be suitable for up to 4,000 audio channels. That's at 48 kilohertz 24-bit. So half that if you're running at 96K. So that's my general recommendation. Yeah, and I saw in the chat there was some discussion about how much percentage of bandwidth is really usable in Ethernet, and yeah, generally you'd get, I think, like I mentioned in the talk, generally you'd get up to 80% before QoS kicks in to regulate the traffic. So you're pretty safe up to 80% when using it with media like audio or video, which is kind of constant bandwidth, a constant bandwidth stream. You know, it may be a little different with Office data, or if you're downloading stuff sometimes, uploading stuff sometimes, which is really variable data, you know, over time. But audio, video is kind of continuous stream. So yeah, up to 80%, up to 400 channels in a gigabit Ethernet. I hope that helps.
Okay, we've got a couple of questions from Ronan here. Is Dante optimization only available in Yamaha Dante certified switches?
Yeah, good question. And actually, it's available in a couple of other types of switch as well, I suppose. It's still a little bit different, but a similar concept. So the other companies that make switches with some kind of optimization that I know of are Luminex from Belgium and Netgear. Netgear makes some specific AV switches that have what they call it profiles, I think. So, and they have a Dante profile, which will set the kind of snooping and QoS for you. So there are a few companies that do that, but perhaps Yamaha is the only one that sort of labels it Dante optimization. But the Yamaha switches also have the Dante presets that will program VLANs for you in various configurations for different things. So yeah, I can't take all the glory for it, but yeah, there are several options. But you can achieve the same thing with regular network switches if you want to take the time to learn how to program them.
Another quick question from Ronan, specifically about Dante virtual sound card not being detected by the Dante network when put on a 10 gigabit Ethernet from the latest to Mac Pros. Is that
right? Yeah, I can't really answer that exactly. That question would need to be directed to Audinate, who make the Dante virtual sound card. It's not a Yamaha product. So Yamaha ships it with certain products, but I don't think the software is compatible with the latest Apple OS. So it might be an OS issue. I'm not too sure. Please check with Audinate support about that one.
Okay. Some nice words from John. We've clearly helped him with his understanding of definitions and terminology, which the industry is yes, it's full of them. Okay, so that's the end of the questions from the audience. There, I'd just like to throw one or two questions at Andy as well, because it's my privilege. I think that throughout the talk, you were talking, all the IP addresses you were referring to were what we call IPv4 addresses. Is V6 making an appearance in the digital audio world?
Not at all. No, not at all. As far as I have seen, it seems to be not necessary. The benefits it brings are too small compared to the added complexity of it. I think most of us in the audio industry wouldn't have the foggiest idea of how to do technical support for IPv6 issues. So no, I think it's well, most of us are only just getting used to version 4 IP, aren't they? and the scope that provides. That gives us a whole load more than we've ever been used to in the last 100 years of audio business. So yeah, the short answer is no.
Okay, well, for the benefit of yes, why as John was saying, is why it took 20 years for IPv6 to make an appearance. So I'm just going to post a link in the chat to the Zoom meeting room, where we can retire to. In days of old, we'd probably go to the bar or to the outside of the lecture theatre and have a pint or two to discuss anything further. So if anybody wants to, I would recommend we all move over to the to that meeting room, and then we can chat in a more informal way with Andy. So for everybody else, it's for me to say thank you very much to Andy for such a great presentation. Thank you very much to the AES UK section for hosting this. And thank you very much to the AES itself for providing the facilities. So thank you very much, and see you next month at the next AES UK talk. So let's give a big thank you to Andy. Thank you.
You're most welcome. Thanks a lot.